Dear colleagues, I am glad to present our study titled Real-Time Adaptive Cleaning of Internet of Things Sensor Data using Machine Learning, Noise Classification, and Rule-Based Refinement. This work was completed by Viktoriia Zhebka, Svitlana Shlyanchak, Svitlana Popereshnyak, and me, Dmytro Nishchemenko. So, as we start, the Internet of Things is generating massive streams of sensor data, particularly from smart home and industrial environments. This data, often univariate time series like temperature, has great potential but is frequently plagued by quality issues such as missing values, outlier sensor drift, constant values, segments, and general noise. This problem can severely degrade the performance of downstream application, making data quality management crucial. Many Internet of Things applications demand real-time processing, meaning traditional batch cleaning methods are often insufficient. It's not enough to simply detect errors. Applications like forecasting or control systems require a complete and corrected time series. Thus, real-time correction is a critical necessity. So, looking at related work, the general idea is that different error types should be handled with specific repair strategies. While machine learning models like random forest are suitable for classification, their explicit use for identifying multiple distinct noise types as a step before adaptive correction is not widely documented in current literature. Much of the existing work focuses on binary anomaly detection, simply identifying data as normal or noisy. Key challenges in this area include defective features, engineering, and the need for accurately labeled training data. Adaptive correction aims to dynamically choose cleaning actions based on the diagnosed noise type. However, existing adaptive methods often differ from our intended approaches. For instance, some methods iteratively refine a single underlying model, or they use statistical triggers without first classifying the noise into multiple types. Implementing sophisticated cleaning techniques in real time also faces constraints such as latency requirements and limited computational resources. While various systems exist, this appears to be a gap concerning methods that explicitly classify multiple distinct noise types using machine learning and then use this classification to dynamically select tailored correction strategies in real time. Our research with URTC aims to contribute to filling this gap. So, our proposed solution is based on classification-driven adaptive cleaning approach. This is further refined by rule-based logic to effectively manage low noise states. The system processes data sequentially, making decisions based on information available within a sliding window of recent data points. As illustrated in a figure on this slide from our paper, the URTCA architecture has several key components that operate iteratively. The first of all is sliding window buffer. This maintains the most recent data points. The buffer provides the necessary historical context. Feature extraction model for each new data point that completes the buffer, a set of statistical features is calculated from the current Windows data. These features aim to capture characteristics that indicate different noise types. Noise classifier. We use a random forest machine learning model, which is trained offline using labeled data with artificially generated noise. Its job is to predict the dominant noise type within the current window based on the extracted features. Rule-based refinement model, distinguishing the low noise states from low amplitude general noise can be challenging for the classifier. Therefore, a rule-based check is applied after classification. If the classifier predicts general noise, but the calculated variance of the current window is below a set threshold, the prediction is changed to clean. And the last, adaptive strategy selection and cleaning operators. Based on the resultant effective label, a specific cleaning strategy is chosen and applied to the current data points. So if data in sliding window in current window was marked as clean, the original data point is passed through without modification. If its marked as outlier, point significantly divides, it's replaced by the Windows median value. Otherwise, if constant value, drift, or general noise, the point is typically replaced by mean or median of the few recent points in the buffer. So if data was marked as missing, it's filled in using the median or recently cleaned values. And now let's talk about experimental stuff. To evaluate URTC's performance, we conducted experiments using a real-world dataset where we introduced synthetic noise. This was done under simulated real-time conditions. The original data came from a real dataset created by sensors in a single home, collected over 14 months at 1 minute intervals. For the study, we focused on one representative data series, indoor temperature. A continuous 1 week segment was selected to serve as a clean ground truth data for our experiments. To create a test set with known errors, we added a controlled mixture of synthetic noise onto this clean ground truth data. We used a fixed random seed for reproducibility. This includes point outliers, constant value segments, drift segments, general noise, missing values. The ground truth and corresponding noisy data sets were split chronologically. The first 70% for training and the last 30% for testing. Now, about comparison methods. We compared the performance against these methods, all operating under the same real simulation. First is the raw noisy test data. Next, rolling median, a common non-adaptive filtering technique, and Kalman filter, a standard model-based filtering technique. The performance of all cleaning methods was evaluated using these metrics: root mean squared error, that is sensitive to large errors, and mean absolute error. It is less sensitive to outliers. To understand the internal classification mechanism, we assessed labeling using overall accuracy, precision recall, F1 score, and the confusion matrix. Now let's move to the experimental results. Our main evaluation focused on the accuracy of data cleaning. On the table in this slide, you can see that it summarizes the metrics for all evaluated methods. As shown in table and visualized with figure, our proposed URTCA method achieved the lowest mean square error and mean absolute error. The implemented Kalman filter, also better than noisy, had more difficulty with the mixed noise types present in our data. To quantify the advantage, table 2 presents the percentage improvement Uh, so URTCA showed a notable reduction of approximately 14% in root mean square error and 23% in mean absolute error compared to the Roman median. The improvement over common filter was about 34% and 67%. Uh, in the paper provides a visual comparison showing how the different methods handled a segment of the noisy test data compared to the ground truth. Visual inspection suggests that URTCA more effectively smooths general noise, corrects outliers, and adapts to shift or constant segments more accurately than the other methods. Uh, Understanding the performance of the internal noise classification mechanism within URTCA also provides valuable insights. We evaluated the accuracy of the effective label compared to the true underlying noise type. The overall accuracy is assigning the correct effective label was approximately 59.7%. So on this figure, we can see that the classification results indicate effective identification and of drift and constant value segments. Method demonstrates high recall for outlier detection, meaning it successfully flags more true outliers. However, the precision for outlier and clean labels is low. This indicates that many segments identified with these labels were actually instances or other noise types, primarily general noise. So, despite this in the underlying classification, particularly the difficulty in distinguishing low-level general noise from true clean segments or certain outliers, we overall the overall URTC architecture achieved superior cleaning performance. This suggests that the combination of adaptive strategy selection and the rule-based handling of low variance states effectively compresses for this classification ambiguous, leading to robust and accurate data correction. So, uh, talking about computational cost, our method required approximately 32.6 milliseconds per data point. This is higher than the Royal median and our common film implementation. However, this processing time is still feasible for many real-time smart home applications involving data sampled at the intervals of seconds or minutes. So, to conclude, this paper addressed to the significant challenge of cleaning single variable time series data from Internet of Things sensors in real time, especially when faced with a mixture of different noise type and anomaly types. Our experimental results based on simulation using real-world temperature data captured with synthetic mixed noise demonstrate the effectiveness of this approach. The primary contribution of the work is demonstrating that an adaptive strategy guided by machine learning-based classification of noise types and augmented with rules can lead more accurate. The significance of this work lies on providing the practical and demonstrably effective real-time cleaning methodology tailored to the complexities of Internet of Things sensor data. The analysis of this internal classification mechanism related that while distinguishing certain noise types remains challenging, the overall adaptive architecture effectively compensates yielding high-quality clean data suitable for reliable downstream applications. However, the study has certain limitations. The internal noise classifier, while effective with the overall system, showed limitations in discriminating some noise types, suggesting room for improvements through the more advanced feature engineering or uh, uh, alternative classification models. Future work should focus on enhancing the noise classification model, extending the framework to multivariate data cleaning, investigating methods for automatic parameter optimization, and finally applying and evaluating the method in specific real-world Internet of Things applications. So, and now, thank you for your attention.